This is Chapter 1, Lesson 3, describing quantitative data with numbers. First, we're going to look at measures of center. What gives us the best measure of center? So the mean is the average. So you take the sum of your observations and divide by the number of observations. So if we had 5 pieces of data, we would add the 5 numbers together and divide by 5. We use x bar as the sample mean, meaning if we determine a mean from the sample that we've drawn, this is how we represent it. Mu, this symbol here, is the population mean. So generally we want to find a sample and find a good x bar as an estimate of the population mean. What we're trying to find out is this usually, what's actually going on with the population. And x bar is our best approximation if we design a good study or experiment for it. So with mean, we want to use these as a measure of center with uniform, symmetrical, and roughly symmetrical distributions, since they give you a good idea of where the data is. When we have skewness, due to the outliers effect on the mean, it tends to be a poor interpretation of where the center is. So the median, which we're representing with capital M up here, is the midpoint of our distribution. So if we put all the numbers in order from left to right, least to greatest, smallest being on the left, largest being on the right, the number in the very middle would be our median. Should we have 2 numbers in the middle, when we have an even number of observations in our data set, then we would take those 2 numbers, add them, and determine their average. So you arrange all numbers in order from least to greatest, find that number in the middle, and that's your median. So if we have an odd number, it's the center number. If the number of observations is even, if the number of observations n is even, and please fix this on your outlines because this was a typo, the median m is the average of the 2 center observations. So we want to use this as a measure of center when there's any skewness present in the graph. If we have a nice bell shape, then we can go with mean. If we have any skewness, then we want to go with the median as our best measure of center. So to give you an idea of what I'm talking about, we're going to do a little conceptual activity here where a red arrow will mark the median, a green arrow will mark the mean of this data set, and then when they're equal, there'll be a single yellow arrow. So let's put in some data. If I have 1 observation here, they're the same, they're both located right here because there's only 1 observation. I have 1 more observation, they're still the same because 2, there'd be an even number. So right here, we can see that they're close. It's not quite yellow, so it's slightly off, although mean and median are very close as their center. Now let's see what happens as we add in some more data points in here. Now you can see they're exactly equal when this goes yellow. So right now they both give us the same measure of center. However, let's see when we start to have a couple outliers. So we have some more data, it's all located around here, they're still the same, but what happens when we get a couple outliers? Now you can see the green arrow, the mean, is being dragged to the right, whereas the red arrow is still right there. So couple of these outliers and we have a bad sense of where the center of the data is. Because of these numbers way out, they affect the mean more. So even if we had a ton of data over here, we could see these outliers still affect it. So this would be skewed right. So with this, the median gives us a better idea of where our true data is because we have some outliers out here, or potential outliers out here that could be affecting us. So when we have any skew like this, we want to use the median, which gives us a better idea of where the center of most of the data is. Lurking variables could be a problem with our outliers. There could be a number of other reasons why, but generally the median would give us a better idea here. So as you just saw, the mean and the median of a roughly symmetric distribution are close together, if not the same, if it's symmetric. In a skewed distribution, the mean gets pulled out. So let's look at an example. In 2009, Major League Baseball had a minimum salary of $400,000. So what that means is most players earn very close to the league minimum, if not the league minimum. If you're a superstar, you get that big contract locked down. So this creates a right skewed distribution because Alex Rodriguez pulled down a big contract. Derek Jeter had a huge contract. Different players that, especially a lot of them on the Yankees because they have a big payroll, end up pulling our mean up to over $3.24 million, whereas the median was $1.15 million. So if you're looking at the average or a typical baseball player from 2009, A typical baseball player did not make $3.24 million because that accounts for all those big contracts in there. A typical one was more by around $1 million. Still a great amount of money and a great salary. However, not nearly as much as the mean. So the median provides a better example here because it accounts for that. Now, one way we measure spread is an IQR, or an interquartile range. So we use this whenever there's skewness because it gives us a better idea of where our data actually lies and gives us far more information than just the median. The median is just one piece of information we get. So an example is here in San Francisco, 57 degrees is our average. Same thing as Springfield, Missouri. However, the two places are really different. If you went to Springfield in the summer, it'd be much hotter than it is here. San Francisco tends to be around the same temperature year-round, a little bit closer to 57, whereas the Springfield, Missouri has a far larger spread because it's colder in this winter, it's hotter in the summer. So that mean doesn't give us a good accurate idea of what the temperature was or what the weather's like. Even the median, if you took it in this case, wouldn't give us enough information to provide us with the distribution of temperatures throughout the year. So for this reason we use interquartile range, a 5-number summary including the minimum, the minimum, the first quartile, the median, the third quartile, and the maximum. So let's talk about what I mean by quartiles. So think about breaking up our data into two halves, the median being in the middle. So then if we looked at each half separately, find the median in that yet again, that would create quartiles, meaning 4 sets of data. The first, we have our numbers ordered from least to greatest. We would have the first quarter of our data, the second quarter, third quarter, and fourth quarter. Hence the name quartiles. So data sets cut in half. Q1, the first quartile, is the median of the first half, meaning the number that covers the first quarter of the total observations including in the data set. So we found our median M, then we look to the left of that, we find the median of that left half. That's Q1. Then we look to the data to the right, and then Q3 is the median of that half to the right of our median of the entire data set. That's Q3. So we just divided the data into fourths. And that's how we find interquartile range. So our interquartile range would be Q3 minus Q1. Now that's important because that's going to help us determine if something's actually an outlier. That determines where the middle half of our data is, because it's like chopping off a quarter from the right, a quarter from the left. Now we multiply that, so we take the range, Q3 minus Q1, multiply it by 1.5. If we have data that is 1.5 times that, greater than Q3, or if we have data that's 1.5 times less than, or data that's 1.5 times less than Q1. So we use this range, 1.5 times it, in order to determine outliers. So if Q3 were 5 and Q1 were 2, our IQR would be 3. 1.5 times 3 is 4.5. So numbers that were 4 bigger than Q3 and 4 smaller than Q1 would be considered outliers. So that's how we mathematically determine an outlier. So a 5-number summary is basically another way to show that. So we have our smallest observation, our minimum, and then we list Q1, and then the median, and then Q3, and then our maximum. So that looks like this on a box plot. What we have in our box is the minimum down here. This second line marks the Q1. Here we have our median. Here we have Q3, and then our maximum. So the first quarter of our observations lie within here. The second quarter within here. Our median is right there in the middle where it's pointed to. Our third quarter of our observations fall within this part of the box plot. And finally our fourth quarter in here. If we had outliers, as we discussed that we'd use the IQR to calculate before, they'd be marked by little dots outside of these whiskers because they would fall outside of the range here. And we'd show that there are outliers in that way. So again, minimum Q1, median, Q3, maximum. So you draw a central box from the first quartile to the third quartile with a vertical line in the box marking the median. If that line doesn't appear, it's because the median either equals Q1 or equals Q3. Whiskers, little vertical lines that mark the smallest and largest observations that are not outliers. Outliers are points that would be marked either to the right of that whisker if it's greater than our maximum value that falls within our range, or to the left if it's less than that. There's some helpful advice on page 61 on how to make a calculator box plot that'll be very useful for you as we move forward and we make box plots, look at 5-number summaries, and a good way to check your work and not have to do it all by hand. Our final measure of spread that we're going to talk about is the standard deviation. So standard deviation is the average distance of all observations from the mean. So you would find the mean of your data set, and then with each of the other observations, each observation, you subtract it from the mean. And then to account for some observations being less than the mean and some being greater, and we're just carried about their distance, not whether they're smaller or greater, just how spread out around the mean they are. We square them, you add them up, and we take the square root. And then finally we divide by n minus 1. The explanation of why we divide by n minus 1 and not n is a little involved and not covered on the AP test, but the main reason is because what we're finding is frequently the standard deviation of our sample, which we use to estimate the population mean. And since it's only an estimate, and because it's generated, the mean's generated from our data set of that estimate, it usually underestimates it. So we divide by n minus 1 instead of n. So our formula looks like this. So variance is sx squared here, and we sum up all of x bars, the mean here. We subtract each number from the mean, square it, add them all up, divide by n minus 1. We take the square root of that to find the standard deviation. So down here we have the standard deviation. Up here we call this variance. So the variance is the same thing as it's the standard deviation squared. Page 65 has more help with this, and we're going to be doing some work on this in our work packet in class. But keeping in mind that standard deviation is basically the average distance from the mean of all of your data sets. So it tells you about how far apart everything is from the mean. So the bigger it is, the further apart the spread is, the smaller it is, the less the spread is from the mean. So that then begs the question, what do we choose? We have two different measures of center, mean or median, and two different measures of spread, IQR, which involves the 5-number summary and the box plot, or standard deviation, which gives you an average distance from the mean. So when we have a reasonably symmetric or symmetric distribution, we go with the mean and the standard deviation. It'll work for uniform distributions as well. When we have a skewed distribution, we want to use the median and the IQR, as they give us much more information than do the mean and standard deviation. So again, because the mean's pulled by outliers in that tail that is present in the skewed graph, we want to use median when they're skew. The IQR we also want to use because standard deviation is just another average. It's the average of the distance from each data point to the mean. So because mean and standard deviation are both averages of some sort, they don't give us as rich information when there's skewness present. So we want to use mean and standard deviation if we have a nice bell shape or uniform shape, or if it's close to that, approximately symmetric. Median and IQR are much, much better if there's any skewness. Finally, that takes us to our multiple choice. So this graph should look familiar, same one we looked at for our multiple choice in lesson 2. But now we're wondering what would be the best way to describe the spread of this distribution. Would it be with the IQR and the median since it's roughly symmetric, the standard deviation and the mean since it's skewed left? The IQR and the median will provide the same information as the standard deviation and the mean, so it doesn't matter. Would it be best to describe it with standard deviation and the mean since it's skewed right, or with IQR and the median since it's skewed right? So take a look at this graph, decide what you think about the shape of it and of its distribution, and then use that as well as what we went over here to think about what would be best here, IQR and median, mean and standard deviation, or it doesn't matter. Also go back and read over lesson 2 in your books and look over that summary, and there's a lot of example problems in there.